Yeah, hello and welcome to the PML School, the Phoenix Modeling Language School. Today we have our final session of the year, and we are starting with a completely new topic, but hopefully we are whetting your appetite for more sessions to come through the next year. Today we want to expand how we are running simulations today. So far in PML School, we have used our models for some simple simulations like, for example, changing the dose amount, or sometimes we've run a multi-dose schedule. And you may remember from last session, Frank Striebel, he showed us a nice trick how to get parameter estimates into the simulations with a covariate statement. So this was nice to see. But you know, with all these simulations that we showed so far, we have covered most of the questions that we receive in Phoenix support. But there was one question that I received earlier this year. It was coming from one of our power users, and his question turned out to be a tough nut to crack. So eventually we got this resolved, but you know, when I was thinking about it a second time, it seemed to me that this actually represented a much more general case. Therefore, I thought it would be a good idea to share this case and its solution within the PML School. To be honest with you, I didn't solve this on my own. I have requested some internal help at Certara. And as you may know, we've got a number of really brilliant scientists, like, for example, you know, Serge Guzi or Venkateshwari Muthukrishnan, to name a few. But for this work, I guess I'm really grateful for my colleague, Michael Tomaszewski. So he provided the solution, and this solution that I've adapted for the PML School, and I'm going to present in today's session. Let me switch. So let me start by explaining the problem. It's a preclinical example, very simple and straightforward to grasp. And the user told me that he had developed an indirect response model that perfectly described his animal data. As you may remember, in PML School, we have covered a series of indirect response models. I guess we call them turnover models. So please take a look at our published materials on our forum if you need more information about this specific type of model. So for this model, the guy had some good population estimates for PK parameters volume and clearance, as well as for PD parameters Emax and EC50. In PML School, we haven't dealt so far with between subject variability, so we didn't cover population analysis. But for this exercise, and to keep it simple, we can view those parameters who are also known as etas, or random effects, that they are there to capture the variability of parameter estimates, and where the assumption is that those random effects show a normal distribution. So this guy had some variability estimates for all his PK and PD parameters. So in altogether, we have two sets: the fixed effects like volume, clearance, Emax, EC50, and then we've got these random effects, as you see here, with a small n in front. That means eta, the Greek symbol eta, eta on volume, eta on clearance, eta on Emax, and eta on EC50. And using all of those parameter estimates, this gave a very good description of the experimental data that he had at hand. What would be the typical next step? Whenever you are in a comfortable situation like this, you can use your model for simulations. And typically these simulations would yield variability in concentrations and effects. But for the project team, these variabilities were not convincing enough to decide on the next step. So let me show this. What would be a convincing argument? Perhaps if you can find out an optimal dose, a desirable dose, but what could that be? perhaps a dose for which 95% of all animals will have reached a particular threshold response. So what you would need to do is to calculate the probability for animals to reach a certain response. But how can we simulate the variability in doses? We would need a function of the concentration and effect that would yield a log normal distribution of the outcome of different doses. This is something that you cannot do with our modeling tools in Phoenix. So we needed to look out for other tools. And what my colleague Mike suggested here is the Trial Simulator Engine, or TSE for short. Let's record. We define a desired outcome, which is to achieve a minimum probability of 95% that animals will reach a therapeutic threshold. And for indirect response models, we can use the ABAC value, which is the area between baseline and effect curve, and this is a common summary parameter for this kind of model that best characterizes the overall effect of the drug. Now for our virtual experiment, we need a protocol, and this experiment, which is in fact a trial simulation, and in this particular case, it is an adaptive trial, although a very simple one. And that has a good reason to keep it simple. We are showing you a completely new tool, and we just want to show you the principal steps here. We don't want to complicate things. So for this trial, we have to come up with the right protocol. What is it? It should be straightforward. We start with an initial dose. Then we use our PK/PD model to simulate the concentration and effect. Next, we check the summary PD response, the ABAC value. And if the target response is achieved, we simply stop. But if that's not been the case, we move on. So we increase the dose in incremental steps and go back to start. And we will continue this loop until we reach our desirable dose. This simple protocol will be executed as our trial simulation run. Before we do that, let's build up the Phoenix modeling code. So in the next slides, I will explain the underlying PML, and then I'm going to demonstrate how to run it. So this, building up the PML code, we are back in our comfort zone. This is all what we have learned over the individual PML School lessons so far. Here, we start with the built-in options. In this case, the population box is kept on, since we want to estimate between subject variability, so we need this box to be checked on. The type of model is a PK indirect model. That's what we choose here. The PK part, which is over here, is kept very simple. One compartment and IV bolus model. And also the PD part is simple. It's an indirect response. In this case, limited simulation of the buildup of a response. For the PK part, we assume a multiplicative residual error model for the indirect model and an additive residual error model. And that's it. So we just keep it as simple as that. You see already the textual code, the PML code, but you can simply switch to the graphical model. And here you see this. You see the PK model on this part with the central compartment, the elimination from the central, and the continuous observation of the concentration. And the concentration is linked with an effect block with all the individual parameters, and this is also linked with an continuous observation of the effect. So next step would be to fit the model to data in order to get final estimates. But to keep it further simple, we are just entering the final estimates for the fixed and the random effects into Phoenix and take those to run the simulations. So let's do that and go to the next slide. So here's the PML code, no surprises here. The differential equations calculate the changes of drug amounts and effects over time. The third differential equation here integrates the area between baseline and effect curve, where the effect is described by E, and the baseline is defined by K in over K out. So by subtracting the former from the latter, we get the ABEC value. And the rest of the code is pretty straightforward and is really common ground. We have as first the sequence statement that initializes our effect to baseline value. Then we have the two residual error models for the concentrations, the multiplicative one, and for the effect, the additive one. Next comes the definition of structural parameters. And we are mainly interested in these. The value of volume, but we know that, and this was actually the case, the reason for the case, we have some variability around this parameter. So we assume a typical value. This is, for example, TVV, always preceding with a TV. A typical value that is specific for the population or the training set in this case. And to this a typical value, we are adding some variability. And this is coming from an exponential function that describes this variability. Now, the fixed effects further down here describes the initial values of the typical values, and these random effects are described here, and they are typically specified in a matrix format. In our case here, again, very simple, we are just using a diagonal structure, so we are assuming no covariances here. Now, the most interesting part of the whole PML code, and you know this should be very familiar from the previous sessions that we had, is the final line, which is an observe one statement. And this actually leads us to the new tool, the trial simulator engine. It will tell trial simulator engine that this parameter belongs to the observed value, this ABEC value. Okay, maybe at this point in time we just go and share an application Phoenix. So, Cheryl, can you see this? Oh. Hello?
Yes.
Okay, thanks. So as I said, I mean, we don't want to fit data today, we're just simulating data. So let me see this is just a small simulation table where you've got an ID. For population analysis, you always need a subject ID or patient ID. So I have this column, time, and the amount that you need for the dose, for the IV bolus dose. So we send this to a Phoenix model object and put it in here. Okay, and here we just need to, leave the population box checked. We are selecting PK Indirect as a type of model. Clearance intravenous one compartment stays the same. We just change here to a multiplicative model. And then as an effect, we use a stimulation of buildup. And that's all what you need. If you go to edit as graphical, you see this one. This is the same graph that we've got before, some PK part and the PD part. And now from here you can actually edit as textual, edit the model as textual, and you see here exactly the same code that we saw on the slides. I mean, I've got some specific initial estimates or final estimates in this case that I can show you in the prepared one. So here you see there are some prepared values already, and we can run a simulation from here, which ends up with PK data like this, a typical, IV bolus simulation. And it will also give you the effect over time. So this is the effect, the response over time for the simulation. Okay, but that's about it from Phoenix. So we can actually take this code. And I've already added this last final bit, this observe1 ABAC, to it, and we can really take this and paste, copy it as a text file and use it for the next step. So let me stop sharing here and go to the next one. Oops. Okay, this was a demo. So this is now the structure of a trial simulation model. And this shows you on the left-hand side the principal structure. And you see there's a top-level domain, which is the main program. And this is actually the one that will execute a single protocol or replicate, so everything below that. With the replicate level, we are defining a series of procedures that produces at the end some observations. So there's an optional level of a site. You know, you can specify different hospitals, if you will. But if you think about animal models, I mean, this is not needed for our animal trial simulation. But then at the next level, we need to recruit subjects, right? So we are recruiting volunteers for the clinical trial, where the individual subjects are picked from a covariate distribution, typically, or from the model itself. And that describes the population in terms of maybe weight, age, disease state, for example. And here again, for our animal trial, we are only dealing with standardized animals, so where there shouldn't be any big differences between demographic variables. So in our case, every subject will be just the same. The variability across animals is already covered in the PK-PD model in form of between subject variabilities, you know, the eta values that I've talked about. But after all subjects have been recruited, or in this case created because it's a virtual experiment, the next phase is a lead-in phase where the subjects are randomized across the different treatment arms. In our simple case, we only have one single treatment, so we don't need any randomization. The final step of the protocol is just the recording of treatments, observations, and these are linked with our PK-PD models that will generate the concentration and effect data. So this is a principal structure of a trial simulation model. How does it look in PML code? And this is a PML code for a very simple trial simulation run. And as you can see, this is just an extension of what we already know from previous sessions. So at the very beginning, the trial simulation asks for a population model which really specifies covariate distribution, the demographics of the data. And we do not have any special populations, so we keep this blank, right? This is just, we don't need to model this. But since this is a required part of element of the trial simulation model, we need to bring it up here. And also with the next step, the join step, this will be joined together with our actual PK-PD model. So this is just what we are doing here. This is a specification of the foundation. The next thing is we are going into some subroutines. And here in the first subroutine or process is the OBS-TRT. This is dealing with observation and treatments. And here it's simple. The first step, an observe statement, we are just looking for the concentration observed from the PK-PD model. And then we wait for a very, very, very small time increment. This is just because we want to observe and apply a dose at the same point in time. We need to put a very tiny time increment between these two. So here in the next line here, we have apply a bolus dose, which is also put in a variable called dose, so we can vary this amount. And then we are coming up with a time interval of 24 hours. This is actually the dosing interval. So we have this coded up as a while in a while loop. so for while the time is less than 24. We sleep for 1 hour. This is our time unit, our increment to record the observations, in this case, the concentration that we get from the PK/PD model. When the time interval is completed, we are recording our summary PD response ABAC value. So this is summarizing the observations and treatments. The next one is just a subject procedure, which just initializes subjects and the observation treatment procedure. The next procedure is a replicate procedure, where we just define the different subjects and different treatment arms. Since we only have a single treatment arm, we set this I arm to 0 and initialize the replication, and then looping over the number of subjects to create those subjects and assign them to a specific treatment arm, in this case just a single one. And then we are left with the main program at the end, which receives some input, like the dose amount and the number of subjects. And what it's doing, it's just calling this replicate procedure to run through. And that is a full trial simulator model in PML. Okay, we do not have a graphical user interface for trial simulator engine. It would make most sense to add this to the Phoenix interface, much like we did with NLME, where you have the built-in options, the graphical model editor, and also the textual PML code entries. But this is not yet available. We will use the trial simulator through a scripting interface. And here RStudio is a very popular one. What you see on this slide is an overview of the RStudio interface, and you have a quadrant view. The main window is split into 4 windows, and this RStudio is installed in the cloud. So you can reach it through our Certara portal, and I will show you this in a minute in the demo. But let me explain the interface a bit. And starting at the bottom right-hand side here, you've got a section for files and folders. These are the files and folders located in the cloud environment, so you can upload files from your local desktop to this folder, and you can export results from the RStudio back to your desktop folder within this files and folder section window. Then the next one is the environment. So here you can see everything, all the variables and output that you produce in R, and you can check and monitor all values, also the arrays that you're producing through R. And on the top left-hand side, this is a source window. Here you place all files like trial simulator models, R scripts, and result files, just to view them, and for the R script files actually to execute them. And I will show you this in the demo how this works. The bottom left-hand side here is a console where you see the interpretation of all the steps that you execute within your R scripts. And it will show you the output as well as warnings and error messages. So in summary, I mean, this is the RStudio is really our interface to trial simulator engine, and we are running our trial simulator models through the application of R scripts. And in the next slide, I'll show you a very simple example of an R script. This is this. Please don't get frightened by this very detailed script that contains way too much text to swallow in this session. Most of the lines really define standard inputs needed for proper execution in this specific R environment, and those lines will never change. And for example, the first part, set up the work environment, this will always stay the same. So you can use this R script maybe as a template, and you just need to change these yellow highlighted spaces. So this one will not change, the work environment. The trial simulator environment, this will also not change on the RStudio instance. But your model file will obviously change. This is something from the files and folders section of RStudio that you simply need to place here. So in this case, we want to just use an indirect simple model file. And the rest, everything that's not highlighted is really coming from the template R scripts that you don't need to change. For example, here, the loading of some libraries that R needs for the R software needs for post-analysis. Also, you don't want to mess up your results directory with lots of files, so you want to clear your results directory, and that will always be the same, so you keep this one. And then, obviously, when you want to run the trial simulation, you need to specify this with this scenario statement, if you will. So the scenario includes the model itself, which is actually defined over here. The output folder is also defined up here. The results directory name is defined here. It's just repeating all the steps. And here you apply the dose. In this case, we give it a dose of 10 units. And this, the final number is just a random seed to start the simulation, to initialize the simulation. Okay, once the scenario is done, a results file has been created. The results have to be read into a certain format. I mean, it's called here the replicate data, or short rep data, into a data frame in R. And this will always be the same. The column names will always be the same, so this will stay the same. But then you are interested in some specific bits and pieces from the results. So that's what we are trying to filter out with the next following 3 steps. So we are filtering out for PK data by piping the rep data and trying to find this PKC ops in this row, and those values get then filtered into the PK data. The same we do with PD data and eBook data. So these are the data that we are going to we are interested in, and we can plot out. All right, that's the R script. I mean, I can imagine that up to now this was a pretty tough session, going through so many textual details. Let me try to demonstrate it now. Maybe this will clear things. So, all right. Cheryl, can you see my screen?
Yes.
Okay, so as I said, we are making available the trial simulator engine through our Certara portal, and here you just need to sign in with your email address. Let me just type it in, and also provide a password. Okay, this will bring me to the portal, and here you've got lots of options that you can pick from to run in a cloud, but we are actually interested in this one, Clinical Trial Simulator Engine, and if you start that, it will open up a new window, the RStudio window. And here you have the files and folders, the environment, and the console, and we are missing the sources, but these sources are picked from here. So here, for example, the eBook folder, these are all the files that I've uploaded. So you can easily upload files from your client through this interface. You just choose a file and you pick for whatever you want to get from here, right? But in this case, we have already uploaded all the files. So we have the indirect simple. This is our PML code, our trial simulator model. You remember this is actually the PD part, and this is where we start with the trial simulator. Additions, subject, replicate procedure, and so forth, and main procedure. So this is the PML code, and for this we need also some R script, and that we can just simply pick from here. And this is the R script as I showed you on the slide, going through this. So, and this is really refers in just here on this path. Yes, we want to run our indirect simple model that I got here in my eBook folder. And the way you do that is you just highlight the pieces that you want to run in R. This is just an interpreter of those statements, and you click on run, and it will run, and it will show you, okay, the output right away. So we want to set up the TSE environment, that's okay. We want to specify the model file, should be okay. And this one has just created a new executable, this TSE. This is actually our PML, our translated PML code into an executable. That's called TSE. Okay, now we need to load some libraries. We can run this here. We can clear the result. There's a results folder here where I've got all my results, like this one, a table. We can clear the results directory with this, so it will remove those. And here we can now run the trial simulation. This is just, using all the specified details from the top and run this as a scenario. So let's run this, and it will create a new file. rep1 CSV. It's a pretty big file. I mean, I can maybe view the file, hopefully. So this is a file, right? It specifies all the inputs like fixed effects, random effects, and so forth. Later on, all the observations that it calculates, like PK ops, PKE ops, and the ABAC values. This is the outcome, the result of the trial simulation. So let's read that into a data frame. And this appears up here. It's just another table, but that is filtered for, just these, the whole information from the run. And now we filter for PK data, that is this one. PK data, it's also just another table. And if you look at the PK data table, you've got here, the type is an observations, scenario, replicate, arm, subject, ID, period, the time, the name, and the value. So here you've got we've got 1,000 subjects. For the 1,000 subjects, and the 24-hour time intervals, the concentrations from the simulation. And the same we do for the PD data. And let's run this. And you have another table here, PD data. And last but not least, ABAC. These are all our ABAC values. Finally, this, I haven't shown this on the slide because it didn't fit the slide. You can easily plot the data. It's really a simple ggplot command where you specify the data, some aesthetics like time and value as your axis, and some line that you will see here. So this is all our IV bonus concentrations. Same for our effects. This is our effect for 1,000 subjects. And then we calculate the area between baseline and effect curve and plot this. And this shows you the distribution of those values. And here's the value, here's the ABAC value, and here's some density showing you the distribution of this value. Okay, this was a simple run, but what we said we were interested in was actually the adaptive trial, the adaptive simulation. We wanted to find out about a desirable dose. So let's go back. We can simply clear all plots here. We don't need those here. We also clear, no, we don't need actually to clear all those. We can just go back here and go to ABAC, and I got another R script called ABAC optimize. It is shown here. It's the same script, right, until this stage here. From here to here, this is different. So I specify an initial dose of 5 units, and I specify a goal achieved value and assign it to 0. And here starts the while loop. As long as this goal achieved value is less than 0.95, this is the probability of the animals to achieve a target ABAC value, which is 3,000. We will construct a parameter for the scenario statement. We just add dose equals the dose value, and add this to the string to run the trial simulation with this dose. Then this is the same as before. We read the data, the results from the trial simulation. We filter for PK, PD, and ABAC data. And then we summarize the ABAC data for this value to be larger than 3,000. This is our target threshold. And then this is a data frame, so I need to just extract one value from it. It's a goal achieved value. And if that's not the case, it will increment the dose in 5 units, dose plus 5, and will go back to the loop. That's what it's doing. So what I can do right now, everything else is initialized. Let's run the whole loop in one go, and this goes like that. And you see in the bottom, it will run all the simulations one by one. You see the dose here in the middle showing you where it is. Then when the dose reached the value of 130 units, it stops. That means the population of 95% is fulfilled in this case. Let's have a look at the plot. Oh no, we haven't. This is the actual plot that we want to see. So we run this plot, and you see now this is this target threshold, 3,000, and you see from the distribution of ABAC values, 5% are below this value and 95% are really beyond this. So this actually concludes the demo here in RStudio. Let me go back to the slides. Okay, let's see. Just what I'm showing here is the small changes to our initial R script. Once again, you can see, I define an initial dose of 5 units and set the actual criterion to 0 at the beginning. And then I enter into a while loop where the criterion is to be beyond 0.95. And so then I'm constructing the dose parameter for the next step, the scenario. I can just add this to the string and run the simulation. Then I read the data in. This is the same as before. The filtering of the data in the next 3 steps is the same. And this step is new. This is just summarizing the output, the ABAC data for values that are beyond 3,000. And then I'm extracting this from the summary, the goal achieved value, and incrementally add 5 units to the dose, and this is a while loop that is really running the adaptive trial. Okay, and the next one, just a summary of our results. So we were interested in the variability of the doses. And the first picture shows the starting point. So this was an initial dose of 10 units. And here they calculated the corresponding ABAC values for such a population, for such a trial. And this plot clearly exemplifies, it's roughly in the middle, 50% below this target threshold, 50% beyond. And then we started the adaptive trial, and the trial reached the optimal dose at 130 units, and this was a final plot where you show the distribution of ABAC values and the vertical bar, which is a target, and this what was a desired outcome. Okay, let's finish the presentation with a brief summary. Today I've presented a new PML tool that is a trial simulator engine, or short TSE. And with a very simple preclinical example, we could see the benefit of applying the trial simulator engine when the question is, what is the optimal dose for the next study? And trial simulator engine is using Phoenix modeling language to define the protocol with all its procedures and functions. And since we should be all fluent in PML, that's what I assume, it shouldn't be a big deal applying our knowledge to trial simulator engine. Right now there is no graphical user interface for TSE, and in an ideal scenario it would be embedded into Phoenix, but as it stands now, we are using RStudio as a surrogate for that. So RStudio requires a bit of scripting, but as I showed you, this is in principle not too difficult. I mean, we are providing templates here, so it should be a really steep learning curve and very quick start with that tool. But the RStudio, with its scripting interface, it offers a pretty high flexibility in dealing with a range of scenarios. So the very simple one that we use today, up to the most complex scenarios you can think of. So I hope this was interesting to you. This is the end of my presentation, and I'm switching over to the Q&A session. So please let me know if you've got any questions. You can post those to the console on the right-hand side of the WebEx window. As of now, I don't see any question. I'm just waiting maybe a bit of time if any question come up. If there are no questions, I mean, what I propose, I mean, you know that we will be uploading the materials to our forum, and maybe you can place your questions or comments there. I'm sending out, oh yeah, when this feature will be in Phoenix. Good question. I don't know. It's up to development to give you an answer on this. But this is something we cannot say right now. What happened to the clinical trial simulators? It was quite a good program. It's still available. The trial simulator, it's a problem, well, the issue with the trial simulator that we have provided so far is the restriction of the Windows operating system. It needs to be a 32-bit system, and it's not simple to handle these days when all computers are equipped with 64-bit systems, but it's still available. What else? Do we have more webinars on this feature, taking a few examples further? That's a very good question. That leads me, actually, please continue to post questions to this, and we, as you know, as usual, we come back with responses in our forum to those. But let me point you to this one thing. Typically, Certara is launching an introductory program for the trial simulator engine, and that will start in January 2018. During a period of time, you can evaluate the tool and get free training with it. And the program comes with an online user guide, and you will get support through our forum. We would then ask you for some feedback on your experience, and we would also offer you further access to trial simulator at a special rate. And so if you're interested, please send an email to sales@certara.com with the subject here is Introductory Program, and we will get back to you with more information on that. I just saw this final question here. Will you share the scripts? As I mentioned, I mean, all the programs, all the project files and the scripts will be shared on our forum as usual for the PML School. All right, so let me go on the next slide. Just a reminder, we've accumulated a lot of them. Yeah?
There are some questions in the chat.
Chat, I just see one from Serge Gouzi. Serge Gouzi, he says that he will give 3 webinars explaining in detail how to use the trial simulator as well as the logic behind it. So this was, I guess, a response to one of the questions. But as I had mentioned, I mean, we will publish those answers to all the questions in our forum later on. One thing, yeah, just a reminder for what you see here, the PML School materials. We've accumulated quite a bit of materials, so you have access through either our forum, which is shown here as a link, and we also publish the recorded sessions on our YouTube channel. And finally, this is the plan for 2018. We will start with a new series where I'm presenting popular models created with non-mem package and how this is translated into Phoenix NLME. And with that, I want to close and thank you for your continued interest. I wish you a happy holiday season, a great start into the new year, and hopefully see you then in 2018. Bye for now.